All right, for decades now, we've been on this massive hunt for dark matter. This invisible stuff that's supposed to make up, what, 85% of all the matter in the universe? But what if we've been chasing a ghost this whole time? Today, we're going to dig into a really radical idea. What if dark matter isn't a particle at all, but a whole new property of gravity itself?
You've probably heard this a million times, right? That 95% of our universe is missing. It's all dark matter and dark energy. But this question right here gets to the heart of what we're talking about today. What if it's not missing? What if the problem isn't out there in the cosmos, but right here, in our equations, in our understanding of physics? This is the question that's going to drive this whole explainer.
So, why do we even think dark matter exists in the first place? Well, the evidence starts at what you could call a cosmic crime scene. Galaxies. When astronomers look out at them, they find that galaxies are just breaking the known laws of gravity. Something is way off.
Okay, so the biggest clue, the smoking gun if you will, is how galaxies spin. You see, based on all the stars and gas we can actually see, gravity just shouldn't be strong enough to hold on to the stars on the edges. They're moving so incredibly fast, they should be flying off into deep space. But they're not. They're just hanging on. Some extra, unseen gravity has to be holding them in place.
And this is where the plot really thickens. We found this super clean, almost suspicious connection between how bright a galaxy is, its normal matter, and how fast it spins. Now, if dark matter were just some random cloud of particles that the galaxy fell into, you'd expect that relationship to be all over the place, really messy, but it's not. It's so precise, it's almost like the normal matter is somehow creating its own extra gravity.
And then there's this other huge problem for the Standard Model. It predicts that our own Milky Way should be surrounded by thousands of tiny satellite galaxies. But when we actually go and count them, we only find a few dozen. And I mean, we're not talking about a small rounding error here. This is a massive gaping hole in the theory. So where are all the missing galaxies?
So this really sets up the central debate. For decades, the main suspect has been some new kind of invisible particle. That's the dark matter theory. But this radical alternative asks a different question. What if we aren't missing a thing? What if we're just missing a piece of the puzzle and how we understand gravity itself? Okay, so this brings us to a totally new framework. It drops a new clue into our investigation, something called the coherence shadow. And it suggests we've been looking for the answers in all the wrong places.
And this right here, this is the heart of it. It's a total game changer. The idea is that the extra gravity we see isn't coming from some invisible particles, but from the pattern of the matter we can already see, from its organization.
So what is this coherence shadow? Well, the best way to wrap your head around it is to think of it like a gravitational echo. Imagine a bell that keeps humming long after you strike it. The idea is that a stable, organized system, like a galaxy spinning for billions of years, generates its own persistent gravitational effect, an echo, based on its own long, stable history. Here's the breakdown of how it's supposed to work. First, you get normal matter organizing itself into something stable, like that spinning disk of a galaxy. Then, over billions of years, that creates what the theory calls a coherent history, a persistent, stable pattern. And finally, that pattern itself generates its own extra gravitational field. That's the coherence shadow. It's not something added on top, it's a direct product of the system's own history.
Okay, cool idea. But does it actually work? Does this coherence shadow thing actually solve any of our cosmic puzzles? Let's apply this new clue to the evidence and see if it can crack the case.
Let's start with puzzle number 1, those thousands of missing satellite galaxies that the Standard Model says should be there. Where are they?
Let's just put these two theories side by side. The standard dark matter model, it predicts thousands of these dark matter halos, which should mean thousands of little galaxies. But what we see? A couple dozen, maybe. Now look at the coherence shadow framework. It says the extra gravity only shows up where normal matter has gotten organized. No organized matter, no dark matter effect. And just like that, the prediction perfectly matches what we see in the sky.
And that's the brilliant part. The satellites aren't missing because, well, they were never there to begin with. The so-called dark matter halo is just the gravitational shadow being cast by the galaxy. If there's no normal matter galaxy to cast a shadow, then there's no shadow. It's that simple.
All right, here's another real head-scratcher for the Standard Model. Astronomers find these little dwarf galaxies that have basically the same number of stars, but some seem to be packed with dark matter, while others have barely any. How is that possible if they're all supposed to be sitting in similar dark matter halos?
This framework has a beautiful answer.
It's not about the mass, it's all about the history. See, a galaxy that has a nice, peaceful history, forming calmly over billions of years, builds up a really stable, coherent pattern. And that creates a strong, coherent shadow, a big dark matter effect. But a galaxy that was born out of violent, chaotic mergers, its history is all scrambled, its pattern is weak, so its dark matter effect is weak. This diversity isn't a problem for the theory, it's a direct prediction.
Okay, I know what you're thinking, but what about the bullet cluster? That's the ultimate gotcha, right? The smoking gun proof for particle dark matter, because it looks like the extra gravity got separated from the normal matter. How can a shadow do that?
The answer this theory gives is, well, it's pretty mind-bending. The idea is that the massive shockwave from the collision acted like a memory wipe for all the hot gas. It completely scrambled its coherent history, basically erasing its shadow. But the stars? They just pass right through each other without interacting. Their history and their shadow stayed perfectly intact. So what we're seeing isn't dark matter separating from normal matter. It's a gravitational effect separating from the matter that lost its memory.
Look, any good scientific idea has to do more than just clean up old messes. It has to make new predictions, things we can actually go out and test. And that's exactly what this framework does. It lays out a clear path for the next investigation.
And these predictions are bold. First, it says that all those giant, expensive particle dark matter detectors, they're going to keep finding nothing. Second, it predicts that we can actually figure out a galaxy's dark matter content just by looking at its age and how stable its history has been. And maybe the most daring prediction of all, it claims to have an answer for another one of the biggest problems in cosmology today. And that problem is the Hubble tension, this massive disagreement over how fast the universe is actually expanding. This framework makes a stunning claim that tension isn't a mistake. It's actual evidence that a fundamental constant of nature is evolving as the universe gets bigger. The theory is basically saying that the laws of physics themselves might not be so constant after all, linking the spin of a single galaxy to the ultimate fate of the entire cosmos.
So let's just boil it all down. The big takeaway here is this. What we've been calling dark matter might not be some extra ingredient we need to add to the universe. Instead, it could be an emergent property, something that arises naturally from the long, complex, organized history of the normal matter we've known about all along.
And that leaves us with one final, really provocative thought. For more than 40 years, we've poured billions of dollars and countless careers into the search for a new particle. This new idea forces us to ask a simple, powerful question. Have we been searching for the wrong thing entirely?